So we're moving into the section of your course where we're going to deal with some physics concepts. Now, to be honest, electricity, which you've already done, is a physics concept. But it's maybe not the traditional physics that you've had if you've had physics through high school. So this section should take you back, if you're from PEI, grade 10 science, you would have started this. And then grade 11 physics, you definitely would have done some of this if you've done grade 11 physics. If you haven't, don't worry about it. This course is designed for people that haven't had physics. If you've had physics, you're going to find it even easier. So we're just going to get some of the key concepts, talk through some of them. We're going to work with a couple simple equations today, and that's going to get you started. Now, the section we're going to deal with today, speed, velocity, and acceleration, those three pieces are not exactly in the syllabus, in the list of outcomes, but because they're essential to understanding force, which is in your outcomes, I like to start with that. So I find it really helps us. And then when we get to talking about fluids, we're going to talk about the speed of fluids. So making sure everybody's on the same page with what is speed, what's velocity, what's acceleration, it's going to help you with some notation. So that's where we're going to start. You may find it maybe a little difficult to necessarily directly relate to your trade today, but we will get there. I assure you we will get there where we relate it a little bit more to the trade. Okay. And if you have any questions at all along the way, or if you're concerned, maybe you haven't had any physics before and you're going, I didn't know we were going to cover physics at all in this course, and you're a little nervous about it, reach out to me. Let me know. I'm here to work with you. Even if we're not in the classroom, I can always do a Zoom session and explain a few things. You'll get through it. I promise you, you will get through it as long as you try to work through those quizzes and reach out to me. So the first thing we're going to talk about is we're going to talk about a couple of terms, and we're going to talk about them today, and then we're going to kind of not worry about it too much. But I want you to know what these words are because I will use them through this lesson. So in physics, there's two types of quantities you can have. One type of quantity is called a vector. A vector is a quantity that has size, magnitude, and it has direction. So this is one of those key pieces. A vector always has a direction linked to it. A scalar quantity doesn't have direction. It's just something that has size, okay? So I could say my desk is, I'd say it's 48 inches long. Looks like it's about that. That's a scalar quantity. It's how big it is. It doesn't have a direction north or south. It's just how large it is. If I told you, on the other hand, that I drove 25 kilometers up west, now I've told you a vector quantity because I've also told you what direction I've driven in. Now, these quantities are going to come up a few times. Today, we're going to talk about vector quantities in terms of velocity is a vector quantity, but speed is a scalar quantity. We'll talk about the difference between them. We use those words interchangeably, but in physics, they're a little bit different. Acceleration is a vector quantity because it has direction. Acceleration, for example, you could be speeding up. That's going to give one type of acceleration. Or if you're slowing down, you get another type of acceleration. That means different directions. If you think about it, if you're coasting down a hill, let's say you're driving and you're coasting up a hill, you know how your car slows down and then it eventually rolls backwards and it speeds up as it rolls backwards. You've got acceleration. Because the acceleration changed your direction, it has a direction associated with it. So it's going to be a vector quantity. And in the next lesson, we're going to talk about force. Force always has a direction. If you think about every push or pull, we'll look at the details of that after. It has direction. The direction in which something is pushed or pulled changes the direction in which it moves. So that's one of those things you can kind of think about. If it's a vector quantity, a vector will always have a direction. A scalar quantity just has a size. It might be what the diameter of a fan blade is. A ceiling fan is. You got a 52-inch ceiling fan, which I happen to have in my living room. That doesn't have a direction. If we say that fan is turning so many revolutions per minute clockwise. Now I just told you a vector quantity because I've also associated direction with the measurement. Okay, so just a couple of kind of definitions so that when the words come up, you actually know what I'm talking about. You know why I'm using them when I'm using them. So the first thing I want to talk about is distance and displacement. We're not going to use these words very much. They're words that are very familiar to us. I'm going to give you the physics definition of them so that when we speak in the same terms. Distance is a scalar quantity. It's the total distance that you've traveled regardless of direction. So if we look at this picture, somebody starts here and they take this long kind of wiggly path over to the end here. Distance is how far they've traveled. And I kind of ignore north and south. You ignore east and west. I could tell you I drove 20 kilometers east and then I drove back home. So 20 kilometers east and then another 20 kilometers back towards west. I live in Summerside. So there's 40 kilometers. I've driven 40 kilometers altogether. That's distance. Displacement is the net distance from the start to the finish. So the net vector distance. And by that, I take into account the directions that I've traveled, thinking how far from where I started did I finish? Well, in the case that I just used of driving 20 kilometers towards Charlottetown and then 20 kilometers back home, I've had no displacement because my directions canceled each other out. I'm right back to where I started. I used to chuckle last year. There was one of the instructors for the gas turbine program. He retired last year, but he loved to walk the hallways and he'd always walk in loops. And I used to, especially when I was teaching with his class, we'd often say he walks all day and he gets nowhere. He puts thousands of steps on, but he gets nowhere. According to physics, his displacement is zero because he always ends up back in front of the same class he started with. Okay, so that's a displacement. So displacement, you'll see displacement is a lot shorter than the distance that's traveled. And that's often the case. You're not going to have to worry about those words a whole lot. We are typically going to use the word displacement when we're doing our calculations because we're going to just kind of think about what's the overall distance and not so much the path in between. But those are the quick physics definitions for you. The reason I give you those two is because when we talk about speed, we're going to have to know those two. Now we'll just do a quick question here, really easy question. I'm going to minimize the screen here. So this question says, what's the distance and displacement represented in the diagram? So one of the ways in physics that we represent direction is we give positive and negative values. Now, by definition, if you are going, by definition in physics, if we're moving towards the right, I always have to think twice about left and right, we're going in a positive direction. If we're moving towards the left, we're going in a negative direction. If you're going up, up is going to be positive and negative is going to be down. That's going to help us out when we get talking about forces. So this is kind of a good ease in with something that's pretty simple. So the first thing we're going to calculate, let's figure out the distance that this person has traveled. So we just learned in the last slide that when I talk about what distance somebody's gone, I'm ignoring the fact that directions will cancel each other out. So we just think about what's the total number of steps, if you want to put it that way. So 0.5 kilometers plus goes back 0.5 kilometers. Notice I'm ignoring the direction. Then another kilometer this way. And then back 1.75 kilometers the other way. So the total distance she's gone is 1 kilometer plus 1 kilometer, 3.75 kilometers. That's the total distance. But when we talk about displacement, we want to cancel out any directions that are opposite each other. So if we look here, I'm just going to go through and label. So we just said if you go to the right, it's positive. So I'm going to put a plus sign on there. If you move to the left, we're going to say it's a negative direction, 0.5 kilometers in the negative. You'll notice positive 0.5 and negative 0.5. I'm going to say they cancel out. We don't even need to write them down because she's right back where she started. From where there, she goes 1 kilometer in this direction, so 1 kilometer positive, and then negative 1.75 kilometers. So the overall displacement, you'll notice 1 kilometer, this kilometer in this direction cancels out with the kilometer in this direction. So the displacement is going to be negative 0.75. The math way we can write that down, we can say, okay, they went positive 0.5 and then negative 0.5. You'll notice that you're just adding them together, they'll cancel out. And then positive 1.0 and then negative 1.75. And we get a displacement of negative 0.75, or we could say 0.75 kilometers to the west. That would be, we could also put directions on. So that's the difference between displacement and distance. Distance includes all of the steps. Displacement is just from, if I take from the starting point to where I end, what is that distance? Okay? We call that displacement. Too many D words, I can get a little bit mixed up, but those are your technical definitions. So when you see those words come up in the future, hopefully you'll remember the difference between the two. Okay, like I said, we will typically use the word displacement, but most of the time we're just looking at one motion at a time. So oftentimes you could use the word displacement and distance and mix them up and still be okay. But this very first lesson, I do like to point out that there is a physics difference between them, because if you're looking for any extra help videos on YouTube, Khan Academy, they will use those specific words. So it helps to know them. I'm kind of giving you I call it physics light, okay? You're getting the light version of physics. So we're going to kind of brush highlights, whereas if you were searching for extra help, you might get a little more detail than you want or than you need from me. All right, we have another two definitions that I want to look at in this lesson, and they're speed and velocity. Now, these are two words that we use interchangeably often. We mean the same thing by them, but in physics, the word we're going to use is velocity, and it does have a little different definition. So I do want to go over the two definitions. So speed takes the total distance you've traveled. Distance was a scalar quantity. It ignores the direction, divided by how long it took for that change to occur. So that's our definition for speed. Change in distance divided by the change in time. We won't calculate speed very often, although we'll often use the word speed instead of velocity just because it tends to click better with our heads. I'll try to use the word velocity where it matters as much as possible to keep things separate for you. Velocity, on the other hand, is a vector quantity. Because it's a vector, it has direction. It uses displacement, and if you remember from just in our last slide, displacement was the distance that takes direction into account. Okay, so it's always going to use that value. So it looks at just the overall path from where something started to where something finished. You don't have to know what happened in the middle. We just want to know from where something starts to where it ends, what's that distance and how long did it take to get there. That's how we figure out velocity. Okay, it always is going to have a direction. So if I'm traveling east, I'm going to have a positive velocity. If I'm traveling west, I have a negative velocity. It's just a way, if you really wanted to, you could redefine the definitions. You just have to make sure whoever you're talking to knows, but those are the conventions used in physics courses. If you were going upwards, we'll say our velocity is positive. If something's falling to the ground, we would say its velocity is negative. Okay, so just some of those key concepts, keywords. Now for units are going to matter for us. And you're probably used to doing speed in kilometers per hour because the speedometer in your car gives you how many kilometers per hour. In physics, we will use meters per second. So you're going to find most of our calculations will use meters per second. That's going to be especially important when we look at calculating an acceleration. Okay, and it says always use base units in calculations. Base units are units without the centi, milli, kilo in front of it. The only time we're going to keep a kilo in front is when we do mass. Okay, how heavy an object is. We're not going to deal with that until we get to our next lesson. The formula for velocity, there's a couple ways you can write it. And this is kind of this is how it's often written. There is another way that I like to write it. And I'll often say velocity is equal to, and I'm going to give you some shortcut notation, the change in distance divided by the time it takes. Velocity is change in distance divided by time. This allows us to easily rearrange using some triangle math. And I'll give you that shortcut if just for those of you that might like it. But this triangle, whenever you put a triangle in front of a letter, it means change in. All right, so here is a question I want you to think about. A car travels around a corner at a constant speed. That means its speed is not changing. It's going, let's say, 75 kilometers per hour. If its speed is constant, so if its speed is not changing, is its velocity also constant, or is the velocity also not changing? Now I have here to give you reasoning in the discussion. I'm going to avoid a discussion for you. It'll save me a little bit of reading and marking time. Remember we said velocity has direction. So whenever you see the word velocity, you should think, direction. So if a car is going around a corner, well, at this point, its velocity is this way. Now it's in this direction. Now it's in this direction. Is its direction changing as it goes around the corner? It better be, or else corners aren't working very well. So if its direction is changing as it goes around the corner, is its velocity changing? Definitely. That's one of the things, and we're not going to deal with that now, and not so much for your course. If we had more time for some of the other courses, we would talk about things like what we call centripetal force, or how force affects an object that's going in a circle, which you guys deal with fans. So that would kind of make sense to deal with that. And one of the reasons why you get force, where you feel like you're sliding in a car, you get that feeling like you're sliding across the back seat. If you don't have a seatbelt on, you got those leather seats. When you go around a corner a little too fast, none of you would have drifted around a corner like that, I'm sure. But the reason why, if you were to do that, you would get that feeling is because you have this velocity that's changing. There's a change in direction as you go around the corner. We're going to talk a little bit about that in our next lesson. We talk about Newton's laws. So when we link force to velocity and force to acceleration. All right, a couple example questions. I want you to calculate a couple things for us. And to calculate them, I'm going to go over the formulas. And I'm going to give you kind of this simple formula. Maybe I should adjust that formula in the slides, but we'll leave it be for now. If you need some help with it, please let me know. So in the 1988 Summer Olympics, I'm going to guess most of you weren't born then. I was not very old. And Alex definitely wasn't born yet. I know how much younger than me he is. In 1988 Summer Olympics, Florence Griffith Joyner won the 100-meter race in a time of 10.54 seconds. Assuming that the distance was laid out to the nearest centimeter so that it's actually 100.00 meters, what's her average velocity? Now you're probably looking at this going, why are they being specific about those zeros? This is really just a question, and you don't have to do sig figs. I've reused this question. That's why it has that info. But it's a question to get us think about how accurate we would be in our measurement. And you'll notice there's 4 digits here, and this one has 5 digits. It's telling us that we should be more accurate in our measurements. So we should give at least 4 digits when we finish the question. Okay? So that's all that is. It's nothing to worry about that way. It's just saying that this 100 meters could not be very accurate, and this is specifying that it is super accurate. So let's say they run 100 meters. So we've got this person, they run 100 meters. Okay, and the time they did it in was 10.54 seconds. So what we need to do is we need to use our formula. So velocity is equal to, an easy way to figure out the formula for velocity, if you don't want to look it up, if its units are meters divided by seconds, it's going to have to be made up of numbers that give us meters and seconds. So that means we have a distance divided by time, and the distance is the change in distance that the person has gone. So if this person started at 0 meters and ran to 100 meters, the change in distance is 100 meters. The time it was done in was 10.54. So 100, and I ditched some decimals here, so I'm going to put it in again. 100 divided by 10.54 leaves us with 9.4876, and we could keep going. I'm writing an extra one on purpose. We need to round. We're going to round to 4 decimal places because that's the number of decimal places in the second. And this 100 meters is saying, okay, be a little bit more accurate. So we'll round to 4 decimal places to match, because the Olympics, the third decimal place, nearest thousandths of a second, just might be the difference between a win and a loss. So we have 9.48. The 7's going to go up to an 8 meters per second. That is per velocity. We don't know if it's left or right, but we know it's all in one direction. Okay? And if it's not given to you, if the 100 meters is positive, you can always assume that your direction is positive unless it says otherwise. We'll do a second example. You begin a trip and record the odometer reading. It says 45,545.8 miles. You drive for 35 minutes. At the end of the time, the odometer reads 45,569.8 miles. What was your average speed in miles per hour? Why would this question use average speed instead of velocity? Well, the reason for it is if you're doing your driving, it doesn't tell, we just know how many kilometers you put on. We don't know how far from home you've ended or how far from your start. So that's why it's a speed. It just uses the total distance, and it's ignoring whether you've gone left or right or east or west, that kind of thing. So that's why we use the word. We're going to calculate things the same way. So speed is the change in distance divided by the time. What is the change in distance? The change in distance is going to be our final distance. So 45,569.8 minus 45,545.8. Subtracting those two leaves us with 24 miles. The time traveled was 35 minutes, but you'll notice we want miles per hour, so we need to change the 35 minutes in 2 hours, and that gives us 0.58. So it's supposed to be an H, not an M. Although I've discovered some of my students write messier than me, so maybe I shouldn't apologize so much. All right, so to figure out the speed, the change in the distance was 24 divided by 0.58 hours. 24 divided by 0.58 leaves us with 41.3 miles per hour. Now, I kind of look back, the question didn't say where to round to, and the way we figure out where to round to is we look, what's the smallest number of digits? So we have two digits there, and we look specifically at things that aren't zeros. So here, there's the smallest number of digits, so 2 digits, so we're going to round it to 41 miles per hour. I won't take off any points for rounding like that, but it is a good habit to think about, does it make sense to round to a smaller number of decimals? And if you think about it, I mean, does your car ever tell you 41.3 miles per hour? Secondly, if you ever get pulled over and a cop tells you were 41.3 miles per hour or whatever, the 0.3, they don't have guns that are that accurate, because your speedometer might not be quite that accurate. You can have that much variation. Actually, they say there's about 5 kilometers per hour variation in your speedometer. I don't know if that's good or bad. That's what I've been told, rumor. So sometimes it makes sense that we would just round to the nearest mile per hour, the nearest kilometer per hour. Okay, one more question, and then I'm going to talk about acceleration. A high-speed train travels from Paris to Lyons at an average speed of 227 kilometers per hour. If the trip takes 2 hours, how far is it between the two cities? Just rearranging the same question. So we know speed is 227 kilometers per hour. The trip takes 2 hours, so time is equal to 2 hours. And we want to know, what's the distance? So, and I've used the word speed. You could use V if you want. It'll give you this, the formula works out the same way. So speed is equal to distance divided by time. We know what the speed was, so we can put that in. 227 is equal to distance divided by 2 hours. In order to rearrange, multiply both sides by 2. And we get 454 kilometers is equal to the distance. I know this might not seem like it necessarily is directly related to the trade, but I assure you, I have tried other years to skip this step, and it's resulted in far more questions later on than if I just discussed it and went through it, took a class, went through it, took one lesson, and went through it at the beginning. So bear with me, it will become useful to you later. If nothing else, just useful for the sake of understanding how the numbers work together and how the relationships work. Okay? It's even good practice for rearranging. So I apologize and I don't apologize all at the same time. Now that we've talked about speed and velocity, the last piece we need to talk about before we dive into forces is acceleration. Acceleration, like I said before, is a vector quantity. It's how fast velocity is changing, and because velocity has direction, acceleration has direction. Typically, if an acceleration is positive, something is speeding up, so the velocity is increasing. And if it has a negative velocity, something is negative acceleration, something is decreasing in velocity. There are exceptions to that. So for example, if an object is dropped from the roof, it's falling down, it technically is accelerating in a negative direction because it's accelerating down, and you know it's actually speeding up as it goes towards the ground. So that's maybe an exception to that rule, but in general, you can use that, especially if you're thinking about vehicles and that kind of thing, okay? But if something's moving in a negative direction, speeding up, it actually means it has a negative acceleration. One of those things that I don't know if that makes it easier to understand or not. Now, acceleration is always in meters per second squared, always. Okay? The reason we do acceleration in meters per second squared, we never do acceleration in kilometers per hour squared, is because you accelerate over short times. Because you accelerate over a short period of time and over a short distance, we do meters per second squared. The formula for acceleration is the change in velocity, so our final velocity minus our starting velocity. This is a velocity at time 0, that's what that means. And our initial time versus the time that when we started. Now, the easiest way I think to write this one is acceleration is equal to the change in velocity divided by time. That's how I honestly prefer to write it. This is the technical definition, but this is maybe the useful rearranging version. So back to that question, is it possible for a car to be traveling at a constant speed and still accelerating? Remember the racetrack? The car going around a corner? It was going at a constant speed, but the direction was changing. Its velocity was changing. Because its velocity was changing, the direction of its velocity was changing, it actually means it's accelerating. Kind of a weird concept, but it is accelerating. That acceleration is part of the force that you feel that pulls you when you go around a corner. Acceleration and force go together really well. Force is the next lesson. That's why we've got acceleration now. All right, so just a couple of questions. I want you to calculate some acceleration so we can see what happens, see how it affects our velocity. So if a car traveling at 5 meters per second, it increases its velocity to 25 meters per second in 8 seconds. What is the car's acceleration? So acceleration, I'm going to use my easier formula. Acceleration, and it means the same thing, is the, oops, I almost wrote time, is the change, that's what our triangle means, change in velocity divided by time. So what is the change in velocity of this car? Well, it starts at 5 meters per second and ends at 25. So the difference, 25 minus 5, you always do the final velocity minus the initial one, is 20 meters per second. This is positive because it increased in speed 20 meters per second. So we can put that into our formula, 20 meters per second divided by 8 seconds leaves us with 2.5 meters per second. Remember I said before, if it's speeding up, its acceleration will be positive? Well, it's speeding up and we have a positive acceleration. Next question, a car is at rest. So if a car is at rest, one of the things to think about, rest means it's not moving. That's the same as 0 meters per second. Good thing to take note of. A car at rest accelerates at 2.5 meters per second squared for 12 seconds. How fast is it going? Well, let's think of the formula. Acceleration is equal to the change in velocity divided by time. If we can find out the change in velocity, we can figure out how fast it's going. We're just going to add that to whatever it was going at the beginning. Or if it's negative, we subtract it. So let's plug in some numbers. So acceleration is equal to 2.5. This is a physics habit of mine, is writing out the variables at the side. So we have acceleration and time. So I'm going to put them in. 2.5 meters per second squared is equal to our change in velocity divided by 12 seconds. In order to rearrange it, we've got 12 seconds on the bottom, so we're going to multiply both sides by 12 seconds. And the change in velocity is equal to 30 meters per second. So the velocity at the end is 0 plus 30. So it is going 30 meters per second. I mean, probably hardly need to write that last step, but that helps explain it. So the velocity that we were going at the beginning plus the change. Next, a car that's traveling 90 kilometers per hour slows down and stops in 8 seconds. What is the acceleration? This is one when I was doing my key up, I did it in the other one and not this one. I didn't do a conversion. We'll do the conversion together. It's an easy conversion to do, and you guys know how to do conversions. So you'll notice in this question, we have unit issues. So acceleration is always measured in meters per second squared, which means velocity needs to be in meters per second squared, or the change in velocity, and time needs to be in seconds. Well, we know we have 8 seconds for time. We don't know what the acceleration is, and change in velocity. Well, it goes from 90 kilometers to an hour to a stop. So its change is, it changes by 90 kilometers per hour, but what is that in meters per second? So let's do a conversion. We'll do it down here. 90 kilometers per hour. How do I convert that? It's actually quite easy to do. We're going to multiply by a bunch of fractions. I want to turn this kilometers into meters. How do you turn kilometers to meters? Multiply by 1,000. There's 1,000 meters in 1 kilometer. Okay, so that cancels the kilometers out, and that's equal to 90,000 kilometers. Oops, not kilometers, meters. Oops. Meters per hour. Now I want to get rid of the hours. Well, if I go 90,000 meters in 1 hour, how many seconds are in an hour? There's 60 seconds in a minute times 60 seconds in an hour gives you 3,600 seconds in 1 hour, which gives us 90 divided by 36. Sorry, 90,000 gives, help if I left all the right zeros on, 25 meters per second. Okay, if it goes from 25 meters per second to 0, the change in velocity is 25 meters per second. Okay, so acceleration is equal to velocity divided by time, the change in velocity, which is equal to 25 meters per second divided by 8 seconds, which leaves us with 3.1. I'll keep, you could go 3 or 3.1. There's only one digit here, no more than 2 decimal places on this, meters per second squared. The hardest part of this one was doing the conversion. That was just a little extra thrown in there because of one of the other classes needs to have those conversions. You don't need it as much, so you won't see it as often. Example 4, how long would it take a car that starts at rest and accelerates at 2.8 meters per second squared to reach a velocity of 80 kilometers per hour or 22 meters per second? I've intentionally put the conversion in here just to save a little bit of work. Well, let's list what we need to calculate acceleration. So acceleration is equal to the change in velocity divided by time. I want to know how long, so I'm looking for time. So time is what I'm looking for. Acceleration is 2.8 meters per second squared. And the change in velocity is, it starts at 0 and ends at 22 meters per second. So the change is 22 meters per second. Speeding up, so it's a positive change. Well, let's calculate. 2.8 meters per second squared is equal to 22 meters per second divided by time. How do you rearrange it? This is one of those ones that people make mistakes rearranging. I am going to multiply by time on both sides. Time times 2.8 equals 22. Oops, that's not a meters per second squared. The square goes on the other side. I'm starting to get too sleepy to be recording stuff. And then we're going to divide by 2.8. Now you'll notice that meters per second squared, I'm going to just say this because I know I had other students that got stuck with it. This meters per second squared, that's just the unit. If you leave the unit out, you could do that. That does not mean we square the 2.8. That's just a unit. We don't do any squaring. That just tells me the type of units that are involved. Okay, that's a mistake some people make. So the time it takes to accelerate this is accelerate to 22 meters per second or 80 kilometers per hour would be 7.8 seconds. Okay. So it's not difficult to work with the formulas. If you're accelerating, you're changing your speed. If your speed isn't changing, you're not going to be accelerating. And we're going to look at using those terms when we talk about forces in the next lesson. So that's what we're working towards. There is a practice sheet that has some easy questions on this for you to give a try. And then there's a short quiz on SAM for you to check your understanding and make sure you understand how to use the terms and do a few calculations with them.